Hello, I'm Dr. Rivette Jones at Capital Technology University and also a student with the Computer Science Department. Today I'm presenting detecting IoT malware with knowledge distillation technique. Okay? Well, so enhancing IoT security with machine learning and knowledge distillation. So the rapid growth of IoT devices has introduced significant security concerns for users and professionals. Malware attacks on IoT devices are on the rise. Digitally security solutions struggle to effectively combat them. Machine learning technique offers potential solution to improve detection, classification, accuracy, and IoT security. However, deploying machine learning models on research-constrained IoT devices poses a challenges due to limitation computational resources or energy constraint. So this is a proposed approach for the knowledge distillation for IoT malware detection. So knowledge distillation is a compression technique that transfers knowledge from complex model to a simpler one. The proposed approach uses a large deep neural network to detect malware and IoT traffic. Knowledge distillation is employed to transfer the knowledge learned by the large model to smaller or more efficient model. This approach improves malware detection, accuracy, reduces computational and energy requirement, or enhance the model robustness against adversary attacks. Deep neural networks are known to outperform traditional machine learning models in various domains, making them suitable for capturing complex patterns in IoT traffic. Knowledge distillation enables the deployment of model on resource-constrained IoT devices, addressing the challenges posed by limited computational resource and energy constraint. So we want to move next into the learning-based IoT malware detection. So the IoT devices increases popularity, ambiguity, have made detecting IoT malware a significant challenge. So machine learning techniques have gained traction for IoT malware detection due to their ability to learn patterns and behavior of data. Decision tree, random, we call it forest, SMVM, and DNS are among machine learning algorithms commonly used for IoT malware detection. Proposed by CSMVM, based on PROS, the utility network traffic feature for IoT malware detection. So, concluded that the DNN effectively detect IoT malware and proposed the DNN based approach using CNN and LSTM network. So here's the little different definition. So the SVM is support vector machine. The MLP, multi-layer perception. CNN, convolutional neural network. These are the definitions of what we use as far as the algorithm. Okay. Okay. So we want to talk about the knowledge distillation technique for IoT malware detection. Continue with that. So for the knowledge distillation technique, transfer knowledge from complex model to simpler, computational less expensive. Proposed knowledge distillation for deep neural network, reducing the size, computational complexity while maintaining performance. Utilize knowledge distillation for IoT malware detection, training student model using soft label generated by teacher model. The student model approximates the teacher model behavior by being simpler and more computationally efficient. Okay, so demonstrating their approach achieved to comparable performance to the teacher model while being significantly smaller and faster. Okay, so we want to go down next to the distinguish our work. This is how we distinguish our work. So Our approach in distinguishing itself by employing knowledge distillation to reduce the computational complexity in the memory footprint of model while maintaining high detection accuracy. Unlike previous studies, our approach does not rely on feature engineering, making it more flexible and adaptable to different types of IoT malware and network traffic. The use of IoT 23 dataset and the Melvis dataset allow us to evaluate the performance of our approach on different types of IoT devices and malware. So let's look at the data processing piece of it, okay? So the data processing is essential to preparing the input data for our model. We extract different features from the IoT 23 and the Maven dataset. Network traffic features such as packet length, count, session duration are extracted from the IoT 23 dataset. Static analysis features including the file size, number of session, and API call present are used for the Melvis dataset. Okay, normalization is performed to standardize the feature, ensuring a mean of 0 and a standard deviation of 1. Okay. Knowledge distillation continued. So the teacher-student architect is utilized for knowledge distillation. Okay. So the teacher network is trained on the Mavis dataset, which contains obfuscated Windows executables. Okay. So the student network is trained on the IoT dataset consisting of traffic featuring a commentary of IoT devices. Knowledge distillation aims to transfer the knowledge learned by the teacher network to the student network. Okay, so soft target generated by student network guide the training process, minimize the differences or the difference from the teacher network output. Okay, so the next slide we're going to talk about the defense. All right, defense framework. So we applied this concept to the task by detecting IoT malware, where the teacher network was trained on the Melvis dataset, which contained obfuscated Windows executable, while the student network was trained on the IoT dataset, which contained traffic features from commentary of IoT devices. We utilized pre-trained teacher network to generate soft targets, okay, for the student network, which were used to guide the training process of the students. Okay. So let's talk about assemble learning and model evaluation. So the assembled learning is utilized to enhance the performance of our model. Multiple student network are trained on different subset on the IoT 23 dataset. Prediction from the student network are combined using voting mechanism to improve robustness. More evaluations conducted using metrics like precision, recall, and F1 score to assess performance. The performance of the model is compared with other state-of-art approaches using the same data set. Okay. So let's talk about the data evaluation quickly. All right. So the data evaluation is crucial because it assesses the performance of our proposed method for IoT malware detection. The IoT 23 dataset comprised of traffic feature from 23 different complementary IoT devices. The Melvis dataset contains a obfuscated Windows executable frequency employed by a malware author to invade antivirus detection, we call it, okay? So the performance of on the IoT 23 dataset, let's talk about that. So the performance of a proposed approach on the IoT 23 dataset was assessed through a comparative evaluation. We compared our approach with popular state-of-the-art models such as the random forest or the FVM or the MLP and the CNN. Those are algorithms, okay? These models are commonly used for machine learning tasks, including IoT malware detection. Additionally, we included baseline model trained on the same IoT 23 dataset without knowledge distillation. The evaluation aimed to determine the effectiveness of our approach in comparison an existing method of the baseline model. Okay. Now let's look at the data set next. Okay, the results of the data set. So in table 1 shows the result of our experimental IoT 23 data set. Okay, as seen, our proposed method performed all other state-of-the-art approaches, achieving an accuracy of 98.22%. This is a significant improvement over the baseline model, which achieved a accuracy of only 92.52%. Okay. So we're going to go to the performance results. And so this table shows the experiment of the Mavis data set. As seen, our proposed method achieved about 98.32%, which is significantly improved over the baseline model, which achieved an accuracy of only 92.36%. Our method also outperformed all other state-of-the-art approaches except gradient boosting decision tree, which achieved a slightly higher accuracy of 98.23%. Okay? Now, we want to talk about the limitation of our approach. So, if you see here the performance dependency on a training data set, highlighted that while our approach has shown promising results, it's important to understand the limitation interpret defining accurately. So emphasize at the end of the considering the modern following limitation is practical and generalizability of our approach. Okay. So if you see these 3 different bullets, you see the performance dependency and training data set, the size and the quality of the training that can be impacted by performance approach. While we used a 2 Wiley data set, we talked about that. And then we talked about the reliance on label data. Our approach requires a label data training, which is time consuming, expensive to obtain. Obtaining label data for new and emerging malware threats can be challenging, limiting the practicability or practical to real world scenario. Depending on the accurate and robust teacher model, the performance of our approach is reliant and on accuracy of robustness of teacher model. If the teacher model is not well trained or suffer from overfitting, it may lead to poor performance or a knowledge distillation approach. Okay. Okay, so we're going to continue with our limitation approach. So, our approach assumes that the student model is simpler and a lightweight version suitable for resource-constrained IoT devices. However, there's a possibility that the student model may still require significant computational resource or may not be feasible for deployment on certain devices. Our approach focuses on slowing on detective malware, does not provide mechanism or mitigating or preventing malware spread or damages. Okay. So I want to talk about the future research direction. So, emphasize that addressing the identified limitation is crucial for improving practical and effectiveness of our approach. Highlighted that the future research should focus on expanding the evaluation on diverse data set to understand the generalizability of our approach, exploring alternative method or acquiring labeled data such as active learning or semi-supervised technique, enhancing the training or teaching model to ensure accuracy and robustness, investigating further optimization technique to improve the feasibility of deployment or resource-constrained IoT devices, developing comprehensive solution that combine detection, prevention, or mitigation strategy for IoT malware attacks. Okay. So this is the end of our presentation of detecting IoT malware with knowledge distillation technique. Thank you.